Can the universe delete itself? Physics says yes. It's called vacuum decay. It all depends on a silent tug-of-war between two particles. When we finally measured them and crunched the numbers, we found a shocking result. We asked the universe, are we safe? The answer wasn't yes, and it wasn't no. The answer was, for now. In this documentary, we are going to explain how we discovered this cosmic kill switch and why, in a strange, twisted way, living on the edge of the apocalypse might be the most beautiful thing about being human. To understand how the universe could end in the next second, we first have to understand why it exists in the first place. And to do that, we have to talk about laziness. I don't mean the kind of laziness where you procrastinate on your taxes or skip the gym. I mean physical, fundamental, cosmic laziness. The universe, deep down, is incredibly slothful. It hates holding on to energy. It wants to get rid of it as fast as possible. This is the most golden rule in all of physics. If a system has excess energy, it will do everything in its power to lose it. Think about a ball. If you hold a ball in your hand 3 feet above the ground, that ball is stressed. You can't see the stress, but it is there. By lifting it up against gravity, you have injected it with potential energy. The ball hates this. It wants to be on the ground. The ground is its happy place. So, the moment you open your fingers, what happens? Does the ball hover? Does it fly sideways? No. It falls. And it doesn't fall because it has a personality or a desire to be on the floor. It falls because nature demands that it sheds that potential energy. It converts that potential into motion, kinetic energy, hits the floor, makes a sound, creates a little bit of heat, and then comes to a rest. Once it is lying on the carpet, it has zero potential energy left to give. It is relaxed. It is stable. In physics, we call this state of minimum energy the ground state. Or, if we want to be technical, we call it a vacuum. Now, we have to be very careful with that word. When a normal person hears the word vacuum, they think of a vacuum cleaner, or they think of the empty, airless space between planets. But to a quantum physicist, a vacuum isn't just empty. A vacuum is a region of space that has reached the absolute bottom of the energy scale. It is a space where the ball has hit the floor and stopped rolling. If you are in a true vacuum, you are safe. Why? Because there is nowhere lower to go. You cannot fall off the floor. If our universe is a true vacuum, it means that the laws of physics, gravity, electromagnetism, the nuclear forces, are the floor. They are the final stable configuration of reality. They will last forever because nature has already done its work. It has already become as lazy as it can possibly be. For the last 100 years, since we started unlocking the secrets of the atom, we assumed that our universe was that ball sitting comfortably on the floor. We looked around at the cosmos. We saw that space is cold. We saw that it is dark. We thought, well, this looks pretty low energy to me. This must be the bottom. We built our entire understanding of science on the assumption that we are living in a true vacuum. We assumed the ground was solid rock. But here is where the metaphor gets tricky. Imagine you are a hiker. You are walking down a steep mountain. You are tired. You want to get to sea level. You walk down, and eventually the ground flattens out. You look around, it looks flat. You put your bag down. You set up your tent. You think you've reached the bottom of the valley. But because it is foggy, you can't see the horizon. You don't realize that you aren't at the bottom of the mountain. You're actually stuck in a little dip, a small bowl-shaped depression halfway up the cliff. You feel stable. You can sleep there. You can build a house there. You can raise a family there. But just 20 feet away, hidden by the fog, the edge of the bowl rises up slightly and then drops off into a sheer cliff that goes down another 10,000 feet. You are not on the ground. You are on a ledge. In physics, this deceptive state is called a false vacuum. A false vacuum is a great liar. It mimics a true vacuum perfectly. It looks stable. The laws of physics work. Chemistry works. Life can evolve. But beneath the surface, the entire system is still packed with massive amounts of pent-up potential energy. The ball thinks it is on the floor, but it is actually balancing on a high wire. It is technically stable. We call this metastable. But it is not secure. And the problem with living on a ledge is that you can't stay there forever. Eventually, something slips. Eventually, the wind blows too hard. Eventually, the universe remembers that it is lazy, and it realizes there is a much deeper valley waiting below. If our universe is a false vacuum, it means that everything we see is a temporary glitch. It means that the empty space between the stars isn't actually empty. It is stressed. It is vibrating with the desire to collapse. And if it collapses, the release of energy would be catastrophic. It would be like the hiker's tent suddenly falling those 10,000 feet. But in our case, the tent is the very fabric of reality. For decades, this false vacuum idea was just a ghost story. It was a theoretical curiosity discussed in faculty lounges. We had no way of knowing if we were in the valley or on the ledge. The fog was too thick. We couldn't see the landscape of the universe. We needed a map. We needed to know the shape of the ground we were standing on. And to get that map, we had to find the thing that creates the ground. We had to find the invisible field that dictates the rules of the game. We had to hunt for the Higgs Field. This is where the story shifts from a philosophical worry to a physical threat. Because we didn't just sit around wondering if we were safe. We went out and built a machine to check. We built a cathedral of science underground to pierce the fog and look at the cliff. And what we found down there changed everything. So, if the universe is a ball rolling down a hill, what exactly is the hill? When we say the universe wants to reach the bottom of the valley, what are we actually talking about? We aren't talking about dirt or rock or gravity. We are talking about a field, specifically the Higgs Field. Now, I know what happens when most people hear the words quantum field theory. Their eyes glaze over. It sounds like impossible math. It sounds like something that belongs on a chalkboard at MIT, not in your daily life. But you have to understand this. You need to understand this. Because this field is the only reason you exist. It is the only reason you are a solid object sitting in a chair, rather than a chaotic spray of radiation flying through the cosmos at the speed of light. Forget about particles for a moment. Forget about little billiard balls bouncing around. I want you to imagine that the entire universe, every inch of empty space from the air in front of your nose to the black void between galaxies, is filled with an invisible fluid. Think of it like a cosmic ocean, or a thick, clear syrup. This fluid is everywhere. It permeates everything. You are swimming in it right now. You can't see it, you can't feel it, and you can't taste it, because you were born inside it. It has been there since the beginning of time. This is the Higgs Field. Why does this invisible ocean matter? Because it is the gatekeeper of reality. It decides how the universe is built. You see, when particles try to move through this cosmic molasses, they get bogged down. They meet resistance. They have to push through the fluid to get anywhere. That resistance, that drag against the field, that is what we call mass. Imagine you are trying to run through water that is waist deep. It's hard, right? The water pushes back against your legs. You feel heavy. You move slowly. Now imagine a fish swimming through that same water. It is streamlined. It cuts through the liquid effortlessly. It creates barely any ripple. In this analogy, an electron is the fish. It interacts very lightly with the Higgs field, so it has very little mass. It can zip around the nucleus of an atom with ease. A top quark, which we will talk about later, is like a human trying to run in deep water wearing a suit of armor. It interacts violently with the field. It gets bogged down. It becomes massive and heavy. And a photon, a particle of light, is like a ghost. It doesn't interact with the water at all. It glides right through the ocean without touching it. That is why light has zero mass and can travel at the ultimate speed limit of the universe. This interaction is the glue of the cosmos. If the Higgs field vanished tomorrow, if the ocean suddenly dried up, the resistance would vanish. Suddenly, the electrons in your body would have no mass. They would lose their ability to orbit atoms. They would fly away from your body at the speed of light. Your molecules would instantly disintegrate. The sun would blow apart. All chemistry, all biology, all life would end in a nanosecond. The universe would become a cold, dark soup of flying particles that never touch, never bond, and never build anything. So we owe our lives to this invisible ocean. It is the ground we stand on. But here is the catch. The depth of this ocean, the value of the Higgs field, is not random. It is precise, and it determines the laws of physics. The specific value of the Higgs field is what sets the strength of the weak nuclear force. It sets the mass of the electron. It creates the rules of the game. If that value changes, the rules change. If the molasses suddenly becomes thicker or thinner, the delicate balance of the atom snaps. And this brings us back to the cliff. Remember the ball on the ledge. The position of that ball corresponds to the value of the Higgs field. We need to know, is the Higgs field at its lowest possible setting? Is the ocean as calm as it can possibly be? Or is the field tense? Is it stuck at a high energy value, wanting to drop lower? Is the universe we see the only possible universe, or is it just a temporary configuration? For 40 years, a physicist named Peter Higgs and his colleagues told us this field had to exist. The math didn't work without it, but for 40 years it was just a theory, a scribbling on a piece of paper. We knew the field should be there, but we couldn't see it. We couldn't measure it. We didn't know if we were standing on solid ground or if we were standing on thin ice. To find out, we had to do something drastic. We had to dip a bucket into the invisible ocean and pull out a drop to weigh it. We had to break the universe open and look inside the machinery. Enter the Large Hadron Collider, the LHC. If you want to understand the scale of this machine, you have to abandon normal human measurements. It is the largest, most expensive and most complex machine our species has ever built. It is a 27-kilometer ring of superconducting magnets buried 100 meters beneath the border of France and Switzerland. Inside its pipes, it is colder than deep space. Inside its collision chambers, it is hotter than the center of the sun. It is a cathedral of science, built by 10,000 scientists from 100 different countries, all working together for one singular purpose. Its job is violently simple. It takes protons, the hearts of atoms, and accelerates them. It uses magnets to spin them faster and faster, pumping them with raw kinetic energy until they are traveling at 99.99999% the speed of light. They are moving so fast that they lap the 27-kilometer ring 11,000 times per second. And then we smash them together. Why do we do this? It's like smashing two high-end Swiss watches together to see how the gears work. Except the gears are the building blocks of reality. When these protons collide, the energy is so intense that for a fraction of a second, the conditions of the Big Bang are recreated. We are punching the invisible ocean. We are disturbing the Higgs field. And just like throwing a rock into a pond creates a splash, smashing protons into the Higgs field creates a ripple. If we hit it hard enough, a droplet of the ocean splashes up into reality. That droplet is a particle. We call it the Higgs Boson, the God particle. The scientists at CERN were hunting for this particle for two reasons. First, to prove the field exists. That gets you a Nobel Prize. But second, and much more importantly, to measure its mass. You see, the mass of the Higgs boson gives us the map of the valley. It tells us how stable the vacuum is. Before the LHC turned on, we had a chart. If the Higgs boson was very heavy, over 140 GeV, the math said the universe was stable. We were in the true vacuum. The ball was on the floor. We were safe forever. If the Higgs boson was very light, under 110 GeV, the math said the universe was unstable. So unstable that it should have collapsed billions of years ago. Which is a paradox, since we are here. But there was a third option. A Goldilocks zone, a middle ground, a specific sliver of weight where the universe looks stable but isn't, a weight where the ball can sit on a ledge for billions of years, fooling everyone into thinking it's safe, while secretly waiting to fall. This is the metastable zone. On July 4th, 2012, the world held its breath. The auditoriums at CERN were packed. Elderly physicists who had spent their entire careers chasing this ghost sat in the front row, weeping openly. The Director General took the stage. They announced they had found it. They found the Higgs. Champagne corks popped. It was a triumph of human intelligence. We had finally found the keystone of the universe. But then the theorists went back to their offices. They took the data from the collider. They looked at the number, and the celebration turned into a cold sweat. The mass of the Higgs boson was measured at approximately 125 giga-electron volts, GeV. Now, that number doesn't mean anything to you. It's just a number. But to a theoretical physicist, it was like hearing a floorboard creak in an empty house. They took 125 GeV and plugged it into the equations for the stability of the universe. They drew the graph. They plotted the point. And the dot didn't land in the green safe zone, and it didn't land in the red unstable zone. It landed right on the line, right on the razor's edge. It was the worst possible answer nature could have given us. It suggests that we are living in a metastable state. We are not at the bottom of the valley. We are on a ledge. The ice we are standing on is thick enough to hold us, for now. But it is not solid ground. We are living in a false vacuum. And the cliff is right there, waiting for us. But wait, it gets worse. Because the Higgs boson isn't the only player in this game. It turns out the Higgs has an enemy, a rival particle that is actively trying to push the ball off the ledge. And to understand why the universe hasn't ended yet, we have to look at the cosmic tug-of-war happening inside every atom, between the force that wants to save us and the monster that wants to destroy us. So we have the Higgs boson. We have the God particle. And we know its mass puts us on the edge of a cliff. But the Higgs isn't working alone. To really understand how close we are to the edge, we have to look at the Higgs partner in crime, or more accurately, its mortal enemy. The universe, it turns out, is locked in a silent, invisible tug-of-war that has been going on for 13.8 billion years. On one side of the rope, you have the mass of the Higgs boson. The Higgs is the good guy in this story. Its mass acts as a stabilizer. It tries to keep the universal ball sitting comfortably in the dip. It wants to keep the vacuum energy exactly where it is. It fights to maintain the status quo. On the other side of the rope, pulling in the opposite direction, is the villain, a particle called the top quark. Now, you might remember quarks from high school chemistry. Protons and neutrons are made of up and down quarks. They are tiny, light and friendly. But the top quark is different. The top quark is a monster. It is the heaviest subatomic particle ever discovered by human beings. To give you a sense of scale, a single top quark is roughly as heavy as an entire atom of gold. Think about that. An atom of gold has 79 protons, 79 electrons, and 118 neutrons. It is a massive complex structure. The top quark is a single elementary point. It has no size, no radius. It is a dot. And yet it weighs as much as that entire gold atom. It is a dense knot of raw mass. Because it is so incredibly heavy, the top quark interacts with the Higgs field more violently than anything else in the universe. It thrashes around in the cosmic ocean, creating massive waves. And the math tells us that this thrashing has a destabilizing effect. While the Higgs boson is trying to keep the energy field stable, the top quark is trying to drag it down. It is trying to dig a hole in the ground beneath our feet. It wants to lower the energy of the vacuum. It wants to pull us off the ledge. So, the safety of our entire reality comes down to a simple ratio. The mass of the Higgs versus the mass of the top quark. If the Higgs is heavy enough, it wins the tug of war. It overpowers the top quark, reinforces the ledge, and we are safe forever. If the top quark is too heavy, it wins. It drags the field down, the ledge crumbles, and the universe collapses into the false vacuum. This is why experimental physicists lose sleep at night. This is why we still run the LHC, because we need to know exactly how much the top quark weighs. When we measure these two numbers today, the contest is terrifyingly close. It is practically a stalemate. The two forces are perfectly balanced, holding our reality together by the skin of its teeth. It's like watching two arm wrestlers who are deadlocked. Veins popping, neither side moving an inch. But here is the truly scary part. Our measurements aren't perfect. We have error bars, a tiny margin of uncertainty in our data. If the top quark turns out to be just a tiny bit heavier than our current best estimates, like 1% heavier, then the math changes. It would mean the tug of war is already lost. It would mean that the barrier keeping us on the ledge is much lower than we thought. It implies that the universe isn't just metastable. It is actively vibrating, waiting for the slightest excuse to fall. Now, a rational person might say, okay, so we are on a ledge, and the top quark is trying to pull us off. But there is still a barrier, right? There is still a hill. The ball has to roll over to fall down the cliff. As long as nothing kicks the ball, we should be safe. In the world of classical physics, the world of baseballs and cars and planets, you are absolutely right. To get over a wall, you need enough energy to climb it. If you don't have the energy, you stay put. The ball stays in the bowl. But we don't live in a classical universe. We live in a quantum universe. And in the quantum world, particles don't follow the rules of logic. In the quantum world, particles are allowed to cheat. This brings us to the mechanism of our destruction. How does the universe end if there is a wall protecting us? To answer that, we have to look at one of the strangest phenomena in science: quantum tunneling. Imagine you are locked in a jail cell. The walls are concrete, the door is steel. You don't have a key and you don't have a sledgehammer. In the normal world, you are trapped. You can run at the wall as fast as you want, but you will just bounce off and get a headache. There is zero chance of you getting out. But in the quantum world, you aren't a solid object. You are a particle. And particles behave like waves. They are smears of probability. This means that an electron doesn't have a specific 100% definite location. It is sort of everywhere at once within a certain cloud. Most of that cloud is inside the jail cell, but because the wave is fuzzy, a tiny microscopic tail of that wave extends outside the wall. There is a tiny, non-zero mathematical probability that the electron is actually on the other side of the door. Usually, nothing happens. The electron stays in the cell. But every once in a while, nature rolls the dice. And if the dice land on the right number, the universe snaps its fingers. The electron doesn't climb the wall. It doesn't break the wall. It simply ceases to exist inside the cell and instantaneously reappears outside the cell. It tunnels through the barrier as if it wasn't even there. It ghosts right through solid matter. This sounds like magic, I know, but it is not magic. It is engineering. We use this every day. The sun shines because protons tunnel into each other to fuse. Your smartphone works because electrons tunnel through the transistors in the microchip. Flash memory drives work exclusively by trapping and releasing electrons using tunneling. It is a proven, undeniable fact of reality. But when you apply this rule to the Higgs field, it stops being a cool tech feature and becomes a nightmare. Remember the universal ball sitting on the ledge? There is a barrier, a hill, separating it from the cliff. In a normal world, the ball would have to roll up the hill to fall off. It would need a massive kick of energy, like a black hole collision, to push it over. But because the Higgs field is a quantum system, it doesn't need to climb the hill. It can tunnel through it. This means the catastrophe doesn't require a trigger. It doesn't need a supernova. It doesn't need an alien experiment. It doesn't need the LHC to explode. It can happen spontaneously. At any moment, without any warning, a random patch of space could simply decide to skip the safety rail. The Higgs field, in that one specific spot, realizes, hey, I don't need to stay up here on this high-energy ledge. I can just teleport to the bottom. And so it does. The value of the field drops. The true vacuum is established in a single point, and the moment that happens, the game is over. This event is called nucleation. Think of boiling water. When you heat water, it doesn't all turn to steam at once. It starts with a single bubble, a tiny pocket of gas forming at the bottom of the pot. In our case, the bubble isn't steam. It is a sphere of a completely different universe, a sphere where the laws of physics have been rewritten. And unlike boiling water, where you can turn off the stove, you cannot stop this bubble. Because the interior of the bubble is a lower energy state than the outside, it is more stable. Nature prefers it. Nature wants to be inside the bubble. So the bubble starts to grow. It starts to eat the old universe, our universe, to fuel its expansion. It is a runaway reaction, a geometric sphere of death expanding outward in all directions. And this is where the horror truly begins. Because this isn't just a wall of fire. Fire travels slowly. You can run from fire. This wall moves at the maximum speed limit of the cosmos, and that fact, the speed of the collapse, is what creates the perfect murder. So let's play this scenario out. Let's imagine that somewhere in the universe, perhaps in a dark, empty void between galaxies, or perhaps right next to the planet Mars, the dice roll the wrong way. A single point of the Higgs field tunnels through the barrier. Nucleation occurs. The true vacuum is born. In that instant, a bubble forms. Inside the bubble, the laws of physics are different. Outside, they are normal. And because nature prefers the lower energy state inside, the bubble begins to expand. Now, if this were a Hollywood movie, you would see a dark cloud on the horizon. You would hear a low rumble. Scientists would look at their screens and scream, "It's coming!" The president would give a speech. You would have time to hug your family. But the universe is not a movie. The universe is governed by a strict, unbreakable speed limit, the speed of light. The wall of the vacuum decay bubble expands at exactly the speed of light. Not near it, exactly it. And this leads to a terrifying realization about how we perceive reality. You see, we see things because light bounces off them and hits our eyes. Information travels at the speed of light. If a car is coming toward you, you see it because the light reflects off the bumper and reaches your eyes faster than the car does. You get a warning. But if the car is moving at the speed of light, the image of the car and the car itself are traveling together. They are stacked on top of each other. This means that the news of the destruction arrives at the exact same instant as the destruction itself. There is no causality gap. There is no before. Imagine you are standing in a field, looking up at the sky. Let's say the bubble started at the sun. It takes light 8 minutes to travel from the sun to the earth. For those 8 minutes, the sun is already gone. It has been deleted. But you don't know that. On Earth, you still feel the warmth on your skin. You still see the bright yellow disk. The birds are still singing. Photosynthesis is still happening. You're living in a ghost history. You're safe, happy, and completely ignorant. Then the 8 minutes are up. You don't see the sky turn black. You don't see a wall of fire approaching. You simply cease. Your optic nerve takes a few milliseconds to process visual information. Your brain takes roughly 13 milliseconds to process an image. But the wave passes through your brain in less than a nanosecond. The physical structure of your neurons, the atoms that make up your thoughts, your memories, your fear, is ripped apart and reformatted before your brain can even register that the light has changed. You cannot hear it because sound is too slow. You cannot see it because the light is the killer. You cannot feel it because your nerves are too sluggish. It is the perfect murder. There is no pain. There is no fear. There is no realization of death. One moment, there is a universe teeming with complexity, love, war, and art. And in the very next mathematically distinguishable moment, there is just the bubble. Absolute instant silence. It is not an apocalypse that you experience. It is an apocalypse that unhappens you. But let's step back. Let's assume the bubble has swept over the Earth and moved on, expanding out toward the rest of the galaxy. What is left behind? Is it just a void? Is it nothingness? No. In fact, it might be the most violent place that has ever existed. Remember the potential energy of the ball on the ledge? When the ball falls, that energy doesn't just vanish. Energy cannot be created or destroyed. It can only change forms. When the Higgs field drops from the false vacuum to the true vacuum, it releases a titanic amount of pent-up energy. It is like a cosmic dam breaking. The wall of the bubble is a transition point where potential energy is converted into kinetic energy and heat. So, the interior of the bubble is not empty. It is burning. We are talking about temperatures not seen since the first fraction of a second of the Big Bang. Any matter that the bubble consumes, planets, stars, asteroids, people, is instantly disintegrated. The bonds that hold your atoms together are snapped. The protons and neutrons dissolve. Everything is reduced to a churning, boiling soup of quark-gluon plasma. In a twisted irony, the death of our universe would look almost exactly like the birth of a new one. And as this fire cools down, new things would begin to form. But they wouldn't be our things. Because the Higgs field is now sitting at a new value, the rules of the game have changed. The fundamental constants of nature would be reset. Maybe in this new universe the electron is heavier. Maybe the electromagnetic force is weaker. Maybe atoms can't form at all, and the universe remains a hot soup forever. Or maybe it goes the other way. Maybe the physics of the true vacuum are actually richer than ours. There is a haunting possibility that our universe, the one we cherish, with its stars and chemistry and biology, is actually the bad version. Maybe we are the rough draft, the glitch, the low-resolution copy. And false vacuum decay is just the cosmos trying to upgrade to the final version. Maybe in that new reality, stable structures can form that are far more complex than DNA. Maybe consciousness can exist in forms we can't even comprehend. If life arose in that new vacuum, they would be made of strange alien matter. They would look at the fossilized radiation of our universe, the old vacuum, and they would shudder. They would say, how could anything have lived in that unstable high-energy nightmare? It must have been hell to exist in the false vacuum. They would look at our destruction as a correction, a renovation. We are just the tenants being evicted so the landlord can fix the foundation. Okay, take a deep breath. We have stared into the abyss. We have dismantled reality. We have imagined the ultimate end. Now, let's turn the lights back on. Let's look at the data one last time. Should you actually be worried? Should you stop saving for retirement? Should you panic every time you look at the night sky? The short answer is no. The long answer is no, but you should be grateful. When physicists calculate the probability of the Higgs field tunneling through the barrier today, the numbers are incredibly comforting. The estimated lifetime of our metastable vacuum is roughly 10 to the power of 100 years. That is a 1 followed by 100 zeros. To put that in perspective, the universe is only 13.8 billion years old. 10 to the power of 100 is a number so large that if you wrote it out on a piece of paper, the paper would be wider than the observable universe. It means that the sun will burn out, the Earth will be swallowed, the galaxies will drift apart, and the stars will fade to black long, long before the bubble is likely to form. We are safe. Probably. There is always the chance that our math is wrong. There is always the chance we missed a variable. But worrying about vacuum decay is like worrying about being struck by lightning while winning the lottery on the same day a meteor hits your house. It is theoretically possible, but it is not worth losing sleep over. So why did we just spend an hour talking about it? Why terrify ourselves with the concept of the cosmic guillotine? Because it changes how we look at the world. There is an ancient philosophy called memento mori. It means, remember, you must die. It sounds morbid, but it was never meant to be sad. It was meant to be a tool for clarity. If you know that your time is finite, you stop wasting it. You stop worrying about petty things. You focus on what matters. The false vacuum is a cosmic memento mori. It teaches us that the universe is not a static, eternal stage built for us to act on. It is a dynamic, dangerous living thing. It teaches us that stability is not a guarantee. It is a miracle. The fact that we are here, that the laws of physics are just right, that the top quark isn't slightly heavier, that the Higgs field is holding the line, is a statistical marvel. We are walking on a tightrope over an infinite drop, and somehow, against all odds, we haven't fallen yet. We are the beneficiaries of a fragile peace treaty between the forces of nature. Maybe the bubble is coming. Maybe it's not. We have absolutely no control over it. And in a strange way, that is liberating. If the universe could delete itself at any second, then the only second that truly matters is this one. Right now. The past is gone, lost in that 80 millisecond lag we talked about at the start. The future is not guaranteed. All you have is the now. So look around you. Look at your hand. Look at the light in the room. Feel the gravity holding you to the chair. Trust it. Not because it is permanent, but because it is here today. The lights are still on. The laws of physics are still working. We are still here, for now.